The Lambda CDM or Lambda CDM model is a parametrization of the Big Bang cosmological model in which the universe contains a cosmological constant, denoted by lambda, associated with dark energy, and cold dark matter. It is frequently referred to as the standard model of Big Bang cosmology, because it is the simplest model that provides a reasonably good account of the following properties of the cosmos: the existence and structure of the cosmic microwave background, the large-scale structure and the distribution of galaxies, the abundances of hydrogen, helium, and lithium, the accelerating expansion of the universe observed in the light from distant galaxies and supernovae. The model assumes that general relativity is the correct theory of gravity on cosmological scales. It emerged in the late 1990s as a concordance cosmology, after a period of time when disparate observed properties of the universe appeared mutually inconsistent, and there was no consensus on the makeup of the energy density of the universe. The Lambda CDM model can be extended by adding cosmological inflation, quintessence and other elements that are current areas of speculation and research in cosmology. Some alternative models challenge the assumptions of the Lambda CDM model. Examples of these are modified Newtonian dynamics, modified gravity, and theories of large-scale variations in the matter density of the universe. Overview. Most modern cosmological models are based on the cosmological principle, which states that our observational location in the universe is not unusual or special. On a large enough scale, the universe looks the same in all directions and from every location. The model includes an expansion of metric space that is well documented both as the redshift of prominent spectral absorption or emission lines in the light from distant galaxies and as the time dilation in the light decay of supernova luminosity curves. Both effects are attributed to a Doppler shift in electromagnetic radiation as it travels across expanding space. Although this expansion increases the distance between objects that are not under shared gravitational influence, it does not increase the size of the objects in space. It also allows for distant galaxies to recede from each other at speeds greater than the speed of light. Local expansion is less than the speed of light, but expansion summed across great distances can collectively exceed the speed of light. The letter lambda represents the cosmological constant, which is currently associated with a vacuum energy or dark energy in empty space that is used to explain the contemporary accelerating expansion of space against the attractive effects of gravity. A cosmological constant has negative pressure, which contributes to the stress-energy tensor that, according to the general theory of relativity, causes accelerating expansion. The fraction of the total energy density of our universe that is dark energy is currently, 2015, estimated to be 69.2 plus or minus 1.2% based on Planck satellite data. Cold dark matter is a form of matter introduced in order to account for gravitational effects observed in very large-scale structures that cannot be accounted for by the quantity of observed matter. Dark matter is described as being cold, non-baryonic, dissipationless, and collisionless. The dark matter component is currently, 2013, estimated to constitute about 26.8% of the mass-energy density of the universe. The remaining 4.9%, 2013, comprises all ordinary matter observed as atoms, chemical elements, gas and plasma, the stuff of which visible planets, stars and galaxies are made. Also, the energy density includes a very small fraction in cosmic microwave background radiation, and not more than 0.5% in relic neutrinos. Although very small today, these were much more important in the distant past, dominating the matter at redshift greater than 3200. The model includes a single originating event, the Big Bang, or initial singularity. which was not an explosion but the abrupt appearance of expanding space-time containing radiation at temperatures of around 1015 K. This was immediately followed by an exponential expansion of space by a scale multiplier of 1027 or more, known as cosmic inflation. The early universe remained hot for several 100,000 years, a state that is detectable as a residual cosmic microwave background, or CMB, a very low-energy radiation emanating from all parts of the sky. The Big Bang scenario, with cosmic inflation and standard particle physics, is the only current cosmological model consistent with the observed continuing expansion of space, the observed distribution of lighter elements in the universe, and the spatial texture of minute irregularities in the CMB radiation. Cosmic inflation also addresses the horizon problem in the CMB. Indeed, it seems likely that the universe is larger than the observable particle horizon. The model uses the FLRW metric, the Friedmann equations and the cosmological equations of state to describe the observable universe from right after the inflationary epoch to present and future. Cosmic expansion history. The expansion of the universe is parametrized by a dimensionless scale factor, defined relative to the present day. So, the usual convention in cosmology is that subscript 0 denotes present-day values, so is the current age of the universe. The scale factor is related to the observed redshift of the light emitted at time by the expansion rate is described by the time-dependent Hubble parameter, defined as where is the time derivative of the scale factor. The first Friedmann equation gives the expansion rate in terms of the matter plus radiation density, the curvature, the cosmological constant, and the gravitational constant. A critical density is the present-day density, which gives zero curvature, assuming the cosmological constant is zero, regardless of its actual value. Substituting these conditions to the Friedmann equation gives where is the reduced Hubble constant. If the cosmological constant were actually zero, the critical density would also be the dividing line between eventual recollapse of the universe to a big crunch, or unlimited expansion. Because it is not, the universe is predicted to expand forever regardless of whether the total density is slightly above or below the critical density, though this may not apply if the cosmological constant is time-dependent. It is standard to define the present-day density parameter for various species as the dimensionless ratio where the subscript x is one of B for baryons, C for cold dark matter, rad for radiation, and d or lambda for dark energy. Since the densities of various species scale as different powers of, e.g., for matter etc., the Friedmann equation can be conveniently rewritten in terms of the various density parameters as where W is the equation of state of dark energy, and assuming negligible neutrino mass, the various parameters add up to 1 by construction. In the general case, this is integrated by computer to give the expansion history A and also observable distance redshift relations for any chosen values of the cosmological parameters, which can then be compared with observations such as supernovae and baryon acoustic oscillations. In the minimal 6-parameter Lambda CDM model, it is assumed that curvature is zero in. So this simplifies to observations show that the radiation density is very small today. If this term is neglected, the above has an analytic solution where this is fairly accurate for a greater than 0.01 or t greater than 10 MYR. Solving for gives the present age of the universe in terms of the other parameters. It follows that the transition from decelerating to accelerating expansion occurred when which evaluates to a tilde 0.6 or z tilde 0.66 for the Planck best fit parameters. Historical development. The discovery of the cosmic microwave background in 1965 confirmed a key prediction of the Big Bang cosmology. From that point on, it was generally accepted that the universe started in a hot, dense state and has been expanding over time. The rate of expansion depends on the types of matter and energy present in the universe, and in particular, whether the total density is above or below the so-called critical density. During the 1970s, most attention focused on pure baryonic models, but there were serious challenges explaining the formation of galaxies, given the small anisotropies in the CMB. In the early 1980s, it was realized that this could be resolved if cold dark matter dominated over the baryons, and the theory of cosmic inflation motivated models with critical density. During the 1980s, most research focused on cold dark matter with critical density in matter, around 95% CDM and 5% baryons. These showed success at forming galaxies and clusters of galaxies, but problems remained. Notably, the model required a Hubble constant lower than preferred by observations, and observations around 1988 to 1990 showed more large-scale galaxy clustering than predicted. These difficulties sharpened with the discovery of CMB anisotropy by COBE in 1992, and several modified CDM models, including Lambda CDM and mixed cold plus hot dark matter, came under active consideration through the mid-1990s. The Lambda CDM model then became the leading model following the observations of accelerating expansion in 1998, and was quickly supported by other observations. In 2000, the Boomerang microwave background experiment measured the total density to be close to 100% of critical, whereas in 2001 the 2D-FGRS Galaxy Redshift survey measured the matter density to be near 25%. The large difference between these values supports a positive lambda or dark energy. Much more precise measurements of the microwave background from WMAP in 2003 to 2010 and Planck in 2013 to 2015 have continued to support the model and pin down the parameters, now mostly constrained below 1% uncertainty. There is currently active research into many aspects of the Lambda CDM model, both to refine the parameters and possibly detect deviations. In addition, Lambda CDM has no explicit physical theory for the origin or physical nature of dark matter or dark energy. The nearly scale invariant spectrum of the CMB perturbations and their image across the celestial sphere are believed to result from very small thermal and acoustic irregularities at the point of recombination. A large majority of astronomers and astrophysicists support the Lambda CDM model or close relatives of it, but Milgram, Magor, and Krupa are leading critics, attacking the dark matter portions of the theory from the perspective of galaxy formation models and supporting the alternative MON theory, which requires a modification of the Einstein field equations and the Friedmann equations is seen in proposals such as MOG theory or Tevez theory. Other proposals by theoretical astrophysicists of cosmological alternatives to Einstein's general relativity that attempt to account for dark energy or dark matter include F-gravity, scalar tensor theories such as Galilean theories, Brana cosmologies, the DGP model, and massive gravity and its extensions such as biometric gravity. Successes. In addition to explaining pre-2000 observations, the model has made a number of successful predictions, notably the existence of the baryon acoustic oscillation feature, discovered in 2005 in the predicted location, and the statistics of weak gravitational lensing, first observed in 2000 by several teams. The polarization of the CMB, discovered in 2002 by Dassey, is now a dramatic success. In the 2015 Planck data release, there are 7 observed peaks in the temperature-power spectrum, 6 peaks in the temperature polarization cross-spectrum, and 5 peaks in the polarization spectrum, and all agree with the predictions of Lambda CDM. Challenges. Extensive searches for dark matter particles have so far shown no well-agreed detection. The dark energy may be almost impossible to detect in a laboratory, and its value is unnaturally small compared to naive theoretical predictions. Comparison of the model with observations is very successful on large scales, but may have some problems on sub-galaxy scales, possibly predicting too many dwarf galaxies and too much dark matter in the innermost regions of galaxies. These small scales are harder to resolve in computer simulations, so it is not yet clear whether the problem is the simulation's non-standard properties of dark matter, or a more radical error in the model parameters. The simple Lambda CDM model is based on 6 parameters: physical baryon density parameter, physical dark matter density parameter, the age of the universe, scalar spectral index, curvature fluctuation, amplitude, and reionization optical depth. In accordance with Occam's razor, 6 is the smallest number of parameters needed to give an acceptable fit to current observations. Other possible parameters are fixed at natural values, e.g., total density parameter equals 1.00, dark energy equation of state equals -1. The values of these 6 parameters are mostly not predicted by current theory, except that most versions of cosmic inflation predict the scalar spectral index should be slightly smaller than 1, consistent with the estimated value 0.96. The parameter values, and uncertainties, are estimated using large computer searches to locate the region of parameter space, providing an acceptable match to cosmological observations. From these 6 parameters, the other model values, such as the Hubble constant and the dark energy density, can be readily calculated. Commonly, the set of observations fitted includes the cosmic microwave background anisotropy, the brightness-redshift relation for supernovae, and large-scale galaxy clustering, including the baryon acoustic oscillation feature. Other observations, such as the Hubble constant, the abundance of galaxy clusters, weak gravitational lensing, and globular cluster ages, are generally consistent with these, providing a check of the model, but are less accurately measured at present. Parameter values listed below are from the Planck collaboration. Cosmological parameters: 68% confidence limits for the base Lambda CDM model from Planck CMB. Power spectra, in combination with lensing reconstruction and external data. See also Planck. AB. The physical baryon density parameter, omega BH2, is the baryon density parameter, omega B multiplied by the square of the reduced Hubble constant H equals H0. Likewise for the difference between physical dark matter density parameter and dark matter density parameter. ABCDEA density ρx equals omega x. ρcrit is expressed in terms of the critical density ρcrit, which is the total density of matter energy needed for the universe to be spatially flat. Measurements indicate that the actual total density ρtot is very close if not equal to this value. See below. This is the minimal value allowed by solar and terrestrial neutrino oscillation experiments. From the standard model of particle physics. Calculated from omega BH2 and H equals H0. Calculated from omega CH2 and H equals H0. Calculated from H equals H0, per ρcrit equals 1.87847 times 10⁻26 H2 kilograms m-3. Extended models. Extended models allow one or more of the fixed parameters above to vary, in addition to the basic 6, so these models join smoothly to the basic 6-parameter model in the limit that the additional parameter approach the default values. For example, possible extensions of the simplest Lambda CDM model allow for spatial curvature, or quintessence rather than a cosmological constant where the equation of state of dark energy is allowed to differ from -1. Cosmic inflation predicts tensor fluctuations. Their amplitude is parameterized by the tensor-to-scalar ratio, which is determined by the unknown energy scale of inflation. Other modifications allow hot dark matter in the form of neutrinos more massive than the minimal value, or a running spectral index. The latter is generally not favored by simple cosmic inflation models. Allowing additional variable parameter will generally increase the uncertainties in the standard 6 parameters quoted above, and may also shift the central values slightly. The table below shows results for each of the possible 6+1 scenarios with one additional variable parameter. This indicates that, as of 2015, there is no convincing evidence that any additional parameter is different from its default value. Some researchers have suggested that there is a running spectral index, but no statistically significant study has revealed one. Theoretical expectations suggest that the tensor-to-scalar ratio R should be between 0 and 0.3, and the latest results are now within those limits. Cosmological models are based on the cosmological principle, which states that our observational location in the universe is not unusual or special. On a large enough scale, the universe looks the same in all directions and from every location. The model includes an expansion of metric space that is well documented both as the redshift of prominent spectra. The Lambda CDM or Lambda CDM model is a parametrization of the Big Bang cosmological model in which the universe contains a cosmological constant, denoted by lambda, associated with dark energy, and cold dark matter. It is frequently referred to as the standard model of Big Bang cosmology, because it is the simplest model that provides a reasonably good account of the following properties of the cosmos: the existence and structure of the cosmic microwave background, the large-scale structure and the distribution of galaxies, the abundances of hydrogen, helium, and lithium, the accelerating expansion of the universe observed in the light from distant galaxies and supernovae. The model assumes that general relativity is the correct theory of gravity on cosmological scales. It emerged in the late 1990s as a concordance cosmology, after a period of time when disparate observed properties of the universe appeared mutually inconsistent, and there was no consensus on the makeup of the energy density of the universe. The Lambda CDM model can be extended by adding cosmological inflation, quintessence and other elements that are current areas of speculation and research in cosmology. Some alternative models challenge the assumptions of the Lambda CDM model. Examples of these are modified Newtonian dynamics, modified gravity, and theories of large-scale variations in the matter density of the universe. Overview. Most modern cosmological